here, so you please decrease the font little bit, no?
What I have to decrease?
The font. Actually, it is in PDF format, right?
No,
Yes,
it's
sir.
a PPT format.
Yes, sir. Please make in presentation mode. It is.
Okay. Now it's okay.
Yeah, now it is
Yeah,
perfectly fine.
it's okay,
Right.
sir.
Okay. So good morning. So today I will present a talk on deep learning techniques for medical image processing. As you know, there is a lot of development in the applications of AI for medical image processing. So in today's talk, we will discuss what is a deep learning, and then we will explore its application in the medical field, medical domain. And at the end of the talk, we will focus on COVID-19 detection using deep learning. So this is the agenda for today's talk. So let us start with the deep learning. What is a deep learning? As all of you are aware about the artificial neural network. So artificial neural network is the this idea came from the human brain actually. Okay, people try to mimic human brain. So in human brain there is a neuron, and neuron collects the information from the dendrites. Okay, so that information is collected at the cell body, and if the voltage or received, okay, some of the voltage received from various dendrites is above some threshold, then neuron will be fired. Okay, this is the idea. But in human brain there are millions of neurons. Okay, and so many connections. Okay, interconnections of the neurons. So it's very hard to mimic human brain. Okay, so some part we tried as a part of neural network. So here you can see we have x1, x2, x3. These are the inputs. Okay, and ANN can have many hidden layers, and finally at the output we can use for classification purpose. So it can be a class y1 or y2. Okay, so this is the single neuron. As I told, here dendrites we are replacing by these inputs. Okay, x1, x2, xn. These are the inputs, and these are the weights actually, w1 to wn. And one bias term is also included. And here it's a body cell, and here decision is taken whether neuron should be fired or not. Okay, so you know, artificial intelligence is very broad area, and machine learning is a subdomain of that area, and again a deep learning is a part of the machine learning. Okay, so today we will focus only on the deep learning part and how this can be used for medical image processing applications. So what are the differences of deep learning with the machine learning? So in machine learning, we have to select proper feature extraction blocks, which features to be extracted, that we have to decide in advance. And based on the features extracted, we will have class performance actually. Performance of the classifier depends on the selection of the features. Okay. So that issue is solved in the deep learning. So here there is no need to select the features or extract the features. This thing we have automated using some convolutional neural networks, okay, CNN type of block or convolution type of operation. Those who are in signal processing area, they know the basic convolution operation. So people use that convolution operation to extract the features. So that we are going to see very soon. And deep learning has got interest actually simply because of the development in the hardware. Now we have a very high-speed processing devices, because deep learning is a data intensive processing technique. A lot of data is required, and we need a proper tools to process that. That's all. Because number of computations are more as a result of convolution operation. Okay. So here you can see here in this slide we have considered only two classes, car and not car. So in case of machine learning, we require a special feature extraction block and then classifier. data. So amount of data is a small. That case actually performance is of the machine learning is most of time better, or so we will not get any advantage of the deep learning. But if amount of data is more, then you can see there's a drastic improvement in the performance. Okay, traditional machine learning, you can see there's a plateau, means performance is saturated actually. Beyond that, we cannot improve. But in deep learning, as data increases, performance increases. So based on the data, actually, a lot of data we can process as a part of training phase, and then model learns actually. Okay, so here we require a data and variety of data actually, a variety of variations actually we require in the data. So we'll see those things later on. There are very standard definitions given by a few people. One of them is Jan, who is IEEE Spectrum editor. So he said you could think of deep learning as a building of machine learning machines, say pattern recognition systems or whatever, by assembling lots of modules or elements that are trained the same way. One of the problem with the deep learning is that we don't understand actually, because there are many hidden layers, how data is processed, how features are extracted. Those things are not clear actually. Like machine learning, we know the features, we have their analytical equations, all those things are there. But here we have automated that thing. There's another definition given on the Wikipedia. Is a deep learning is a branch of machine learning based on a set of algorithms that attempt to model high-level abstraction in a data by using a deep graphs with multiple processing layers composed of multiple linear and nonlinear transformations. Okay, so all these terms actually we are going to see. So let us discuss actually why we are interested to use deep learning for medical image analysis, and which domain actually we will use. So in in medical image analysis, we can classify the task actually. So in medical image or medical diagnosis or healthcare purpose, we require a detection or localization. So detection and localization means we want to detect for example, we want to detect the tumor, okay, brain tumor. Okay, so that's why we call it as a detection. Once we detected, actually, a doctor want to remove that tumor by surgery. So to perform surgery, we should know the exact location actually. Very high accuracy in the localization. Otherwise, actually, doctors has to do a surgery, big surgery. Okay. So, and patient will be risk and he will have more pain, all those things. Okay, so detection and localization is one area. Another is a segmentation. So if there is a tumor, then we should know the size of the tumor. So that size information we can get from the segmentation. That also we can segment actually, how much is the tumor, what is the, so the segmentation is another task. Next is the registration and then classification. So registration means actually we can collect different images. For example, in CT scan, we take the images with a different angles actually, okay, around the object, 360-degree angles, okay. So we have many images collected with a different angles. So we can register them and we can model a 3D object, okay. So we can model a tumor or model any body organ, okay. So there we have to stitch these images actually, okay, different images. So that is called as a registration task. And another task is a classification, means the object is there, whether it is a tumor or not tumor. So that way we can classify, okay, whatever region we have extracted, whether it is a tumor or not. So in this way we can have two classes. So this is about the binary classification, but we can have many more classes. Okay, tumor also we can have 3-4 classes, actually, type 1, type 2, type 3, in this way. Okay. So this is about the classification. So all these tasks come under the pattern recognition task. Okay. And deep CNN block. Okay. And that's why if we want to use a deep learning for one dimensional, most of the time people have to convert the one dimensional signal into convenience. Actually, that will help to apply a mask. Okay, CNN masks. So these are different tasks. And anatomical regions, actually, which anatomical regions of human actually we can treat, or we are using the deep learning. So now, so if we survey that, actually, then you will find deep learning is used in the different anatomical regions, and regions are brain, then breast, eye, chest, abdomen, and some miscellaneous regions. So brain region, actually, brain tumor detection is very popular applications. Breast also, we know the breast cancer detection. Eye, people used to detect the diabetes or retina image processing. So that's why eye. Chest, pneumonia detection, for example, or many other diseases. But nowadays, we have witnessed the COVID, actually. So COVID, because of the infection, coronavirus infection, we have seen the infection in the chest. So how much chest is infected, actually, okay, that we can detect using the deep learning techniques. Okay. And for that infection, if we want to know the percentage of the infection, so then we have to go for the segmentation, which part of the chest actually there is an infection. So that for that purpose, we have to use detection on localization block. Okay. So all this task actually we can use for extracting information from the different anatomical regions. Another is the abdomen region. Okay. And some other regions. Okay. So this is the just overview I given, actually, which are the tasks and which anatomical regions we can use this. Okay. Based on the research work during past 10 years, okay, or more, you can see. I have collected some papers also, and based on that, we can have these statistics. You can see here, 2012, 2013, 14, 15, 16. So you can see 16 onwards, there is a lot of use of deep learning in medical image analysis. So there are a large number of papers published in the 2016, then 17, and now people are publishing. Okay. So this is the trend. And so here orange color indicates the CNN. Actually, there are various models we are going to see. So one of them is a CNN. So orange color indicates that CNN is used. Okay, most of the papers they use CNN model, and little bit they used RBM. Then RNN means recurrent neural network. Autoencoders, very less number of papers, and others. Okay, so CNN has used widely, and if we consider the anatomical regions,
Hello. Hello. Jayavardhan sir, am I audible? Hello. आपकी आवाज तो आ रही है। Excuse me, sir. Hello. Sir, sir, please unmute yourself.
Okay.
Yeah,
Now
yeah.
audible. Okay.
Yeah, sir. Now
So
you are
there are
audible.
different modalities. So we are aware about this, that MRI is one modality, then CT scan image, X-ray image, okay, ultrasound images, mammograms. These are the different image modalities used in the healthcare. So you can see here, MRI, actually people used, so you'll find large number of work on MRI, magnetic resonance images. After that, microscopy images, then CT image, then ultrasound, then X-ray. Okay, so from this graph, if you want to select some problem on for your research, then you can understand, okay, that which models are used for the medical image analysis. Then you have to select proper task, actually classification or detection, segmentation. Then you have to select proper modality, image modality. Okay, and then anatomical region, actually if you want to process the brain region or lungs or breast, okay, in this way. So you will get a current trend, actually from these graphs, okay, from this slide. So let us start introducing a deep learning. So what is a CNN? So CNN means convolutional neural network, and um, so neural network, we are aware actually that neural network has one input layer, then hidden layers, and then one output layer. And so that we have studied. Then why it is called as a convolutional neural network? Because here convolution operation is used. So let us see what is this. So let us assume, let us see, this is a small image segment. I have considered 7 pixels by 7 pixels, 7 by 7 image, and 3 by 3 mask. So here this 0, 1 is a binary image. So only 2 intensities are there. And mask is a 3 by 3, and these are the coefficients of the mask. So this is a point operation, okay, point or pixel wise operation. Pixel wise operation means, the image processing means we are going to give image as an input for this block, image processing. And we'll get a output as also image, and that is a processed image. So we want to process the image. So for processing purpose, we are going to use this mask, and all pixels we are going to process. So let us assume the scenario that we want to process this pixel. So what we'll do, we'll actually align this mask, 3 by 3 mask on this. So this intensity of this pixel we want to change. So here the intensity values will be multiplied with the coefficients of the mask. So 0 will be multiplied with 1. So here this blue color indicates the coefficients of the mask. And so there will be multiplications, and then we'll take the sum of that, and we can we'll divide by total number of pixels. So that will give us the processed pixel, okay, intensity of processed pixel. So here you can see 1 multiplied by 1, and so that's why okay, so 1 multiplied by this 1, so 1, so we'll have only 1.
Sir.
Hello.
Sir, excuse me, your screen is not visible, so please reshare it.
Okay. Just again.
Yeah.
Okay, you just keep informing me, okay, whether there's a.
Yeah. Sure. Now, yes, it is visible, but please do it in. Yeah, sir.
Yeah. Okay.
Yeah, the screen
So
of convolution operation is visible, right? That one.
Right. Yeah. Okay.
Okay, sir.
So here, okay, here we have replaced this pixel actually by value 1. In this way, the next time we'll move this mask by 1 location, and then we will have a multiplication, and we have a new number, say like a 2. In this way, we'll keep moving. If we are shifting this mask by 1 location, it is called as a stride 1. If we jump, actually shift the mask actually by location 2, then it is called as a stride 2. In this way, we can process complete image. Here you can see the size is reduced by so 7 by 7 image. Now it's a 5 by 5. Why it is so? Because here we have skipped this boundary pixels. Because boundary, if we place this mask here, then it will be out of the image actually. Okay, so we will not have we don't have the values for that. So that's why it's better to skip. So mask size is a 3 by 3. So that's why first row and last row and first column and last column is skipped. So image is reduced by reduced to 5 by 5 size. Or there is another technique called as a zero padding. So you can consider outside outside the image pixels are 0, and then you can apply the mask. So these are two techniques to handle these problems, alignment of the mask problem. And intentionally size of the mask is selected as a odd number because for alignment actually. Okay, and in summary we can say here we are considering the local neighborhood of the pixel actually. Okay. So when we are putting this mask and taking the corresponding multiplications, so what we are doing, we are taking the effect of neighbors on the pixel actually. So that's why, but we are considering local neighborhood, just one pixel neighbors. Okay, very close neighbors we are considering, and then processing the image. So here there is the effect of neighbors on the pixel. Okay, so this is the convolution operation, and you can see here. So by using that convolution operation, we can process the image, and then we can use a max pooling operation. So why the max pooling operation is used? Because in the deep learning, as I mentioned, it's a competition intensive applications, a lot of competitions actually, because image itself is a big image, usually 256 by 256. Then we are applying the mask actually. We are processing all pixels, each pixel. For each pixel, we require a large number of competitions. Okay. So we have to handle this problem. This is also another challenge in the deep learning. So one of the operations used is this pooling operation. So you can see here by performing pooling, frequently we can perform the pooling actually in our architecture, deep learning architecture. So that will reduce the size. So here image size is 8 by 8 rows, 8 columns and 4 rows, 4 by 8. So that is reduced to 2 by 3 image. So here the block of 4 pixels, we are putting only one value, selecting only one value. So how to select that? So there are simple operations people have used, like average pooling. Average pooling means here 8, 6, 4, 2, we can add and divide by 4, we'll get 5. Or you can avoid this average operation also. So we just select the maximum value of these 4 numbers. So maximum is 8. So here 8 is selected. Then we'll shift this, we'll go to the next block, then 14 is selected, and the next block 10 is selected. In this way you can select. So it is called as a max pooling operation, and this is called as average pooling. What is the difference? Here you can see in average pooling we will find floating numbers. We will get a fractional numbers. Usually intensities we consider integer numbers, actually 0 to 255 intensity values. Okay. So that's why it's better to go for max pooling operation. In average pooling operation, we have to perform another operation here, that we have to round this number. 9.5 you can round to the 10, or 6.25 you can round to the 6. Okay, closest integer. So that we have to decide actually, rounding technique. Okay. So this is about the pooling operation, and you can see. Okay, so max pooling, and so there will be many layers actually. This is a size of the, you see the matrix size 128 by 28 is reduced to 64 by 64. This is just because of the max pooling operations. So after this max pooling operation, we can have again another convolution operation. Then again we can use a max pooling operation to reduce the dimensions. Okay. So why we are doing this couple of times or multiple times? The motivation is each operation actually. Here first convolution operation, we are extracting some features, Then again, we are performing the max pooling operation. Now again, we'll apply a convolution operation on this max pooled matrices. So again, we are extracting features. So we are extracting features multiple times, hierarchical way, so that we can get a very high level features. Okay, initial CNN operations will extract the features like edges, okay, vertical edges, slant edges, boundaries. And as we move towards the right, actually, if we apply more and more CNN layers, convolution operations, we will extract a high level features. Okay, so this is there. There are some activation functions. As I told, actually, in single neuron, we have to take the decision whether neuron has to fire or neuron should not fire. That firing depends on, in your brain, firing depends on the collected voltage. Actually, if it is above threshold, then a neuron will fire. So here some activation functions are used, actually, like this. So these are the functions. So here we will take the decision, like first a red color function. So here we can have decision like if a value is more than 0.5, okay, we can fire or not. Okay, so these functions we'll see. Okay, and then there's a last layer which is called as a fully connected layer, and this layer is used for classification purpose. We have seen CNN used for the feature extraction, and this last layer, it's a fully connected layer, is used for classification purpose. So output neurons of this layer is equal to total number of classes. We are going to see this with some applications. There's another question, actually, how many layers we should use, actually. One of the constraint is hardware or processing time, available hardware. We have to reduce the number of layers. Actually, we cannot go for the infinite layers, like 100 layers, 200 layers, 1000 layers. We cannot go. And secondly, as you know, in artificial neural networks, we use a backpropagation technique to update the weights. And in our backpropagation technique, it's based on the gradient. Actually, we are going to use the gradient. Actually, if number of layers are more, then this gradient starts reducing, and at some point of time it becomes close to 0, and then we cannot have information and we cannot update the weights. Okay, so that is one problem. So this is about the number of layers, actually. So how many layers we should use? So initially, actually, researchers started using 5 layers, okay, less than 5 layers. So that time, that model we call as a shallow model. If number of layers are more than 10, then we have to do a batch normalization or initialization process. And if layers are more than 30 layers, then we have to use the skip connections. We will discuss, actually, all those things. What is this? And layers more than 100, then we have to use identity skip connections. And 1000 means that we have not actually reached to that level. Okay, that is future. So here, if layers are small layer, then you can handle easily. If more layers, then we will face some problem. One of the problem is vanishing gradient problem. Okay, so that problem can be solved, actually, by using a batch normalization or skip connection. Okay, so what is a batch normalization? So training of deep neural network is done by passing data in several mini batches. Okay, so instead of so we will pass the data, we will train the network with the different batches. Okay, that is one technique. Okay, another is a dropout or regularization. This batch analysis helps to solve overfitting problem. And another technique is a dropout regularization. Dropout means every training phase, actually, we are going to drop some neurons or some layers also we can drop. This we have to do because we want to introduce some randomness, some probability actually. If we have a very good high quality of the images, okay, and we train the model, and while testing actually we don't have such a high quality images, then model will confuse actually. Model will not classify that image actually. If there is an image, face image of particular person, and while training we have used very good quality images, but we practically we don't have good quality images, okay. So that time model will say, okay, this person is not the same person which we used during training, but actually the person is same, but because of noise or because of the some problem actually, some variations in the data, variations in the image capturing. So to handle that problem, we can introduce the some randomness or some uncertainty. Okay. So okay, now next is the how many CNN models are there? So there are so many CNN models people propose actually. Okay, and mainly for medical image processing, people use. I have listed some CNN models. So those are AlexNet, then VGG, GoogleNet, ResNet, HighwayNet, DenseNet, ResNext, CNET, okay, NASNet, YOLO, GANS, okay, SiemensNet, UNet, FINET, okay, all these are the models used in the medical image processing. So you have to select the proper model also if you want to start research in this medical field. I have seen some papers on, many papers on UNet also. So those are shown here. So this encoder decoder may, okay, auto encoder actually people are using nowadays. Okay. Then RNNs or ResNet, ResidueNet, you can see this ResidueNet where large number of layers are used. If number of layers are there, then you need a identity. Here you can see input is fed again here, so that gradient will not become zero. Okay, all those things we have to understand. Here you can see ResNet. So these are the layers, but here we are providing the input again here actually. Okay. So ResNet actually. So there was one competition actually started from 2010 actually, and this started because of the ImageNet database. Okay. So ILS VRC stands for video recognition competitions, and I for ImageNet large scale video recognition competitions. So you can see initially people use a shallow network, maybe less than 5 layers. So that time, this is the error actually. Error was 28.2, 25.8, etc. So in 2012, people started. Actually, there was a competitions every year, and in 2012, AlexNet model actually was the winner, and which has used 8 layers, and they got an error up to 16.4. Okay, other models got more errors. So this is the winner actually, AlexNet. So that time, or in 2012, we reached to 16.4 accuracy. In 2013, there was improvement in the model and the same model, and accuracy up to 11.7. Okay, but in 2014, they use actually more number of layers. Okay, so layers, 19 layers, and accuracy error is reduced to 7.3. And VGG model was a winner that time. So then in 2014, GoogleNet actually winner with accuracy 6 error 6.7%. You can see the error is continuously reducing by using more number of layers. But in 2015, actually, ResNet was introduced, and they use very large number of layers. They used 152 layers. Okay, you can see the change actually shifting from 22 layers to 152 layer happened in the 2015. 14, 22 layers, and 15 they use 152 layer, and ResNet was the winner So you can see accuracy, very good accuracy. So error was up to 3.57%. So you can see, but we have paid a very high cost for that actually. This cost is in terms of layers. So you can see the layers increased to 152 from 22 layers. Okay, just 1 year before, 22 layers were used. But people are not least interested about the number of layers. They want more and more accuracy, because nowadays we have very good resources because of parallel computing and hardware, very good hardware. People is for very it depends on the applications. Actually, application is very important. Then people go for the accuracy. Accuracy is more important. And in the medical domain, we have to concern about the accuracy. We should not concern about the cost or hardware, because it's a problem with the life of the person. So that's why people have used or recommended to use more layers, but without compromising the accuracy. So this is the revolution happened in the ResNet. So you can see the revolution in terms of layers, in terms of the accuracy. Okay. And then DenseNet. Okay. So here actually, so DenseNet to have blocks actually X0, X1, etc. blocks, and they keep on giving the input actually. Okay. For this block X1, we have input from X0 block. Okay. But for block X2, there is an input from X1 as well as X0 block. Okay. In this way, we are feeding this input actually, okay, to each block actually, to avoid the vanishing gradient problem. Okay. Always, otherwise, if there is a big sequence, then we will lose the impression of the input. Okay. Only processed outputs if we are using, because processed output contains error. So we have to feed proper input. So just I'm giving the overview. Okay. So after with this introduction, actually, with this introduction of the deep learning, so deep learning, we have seen that there are various models. One of the popular model is CNN. We have seen there are large number of papers on CNN, but other models are like a ResNet, RNN, or even auto encoders. Okay. So these are the models. Now, if you want to start the research, then some programming tips are also given here. So there are various tools actually. Working in deep learning is not that much challenging, because various libraries are already available. And libraries means they have inbuilt functions. So there's no need to write a code. Okay. Just you can use some functions. You should be able to understand the importance of the function, and you can use directly. You should know only the syntax of that function, how to use. Okay. And most of these libraries are actually compatible with the Python or C programming. So one of the popular libraries are TensorFlow. Many people are using TensorFlow, and this was developed by Google Brain. And so this is you should know the Python or C++. Okay, this has a good interface with the Python or C++. Another library is a PyTorch. So Facebook has proposed this library. Okay, and then Cafe2, Keras libraries. Okay, so actually in our lab also students are using TensorFlow, PyTorch, Keras. These three libraries are very popular. Okay, then there are libraries such as a MatConvNet. Okay, as name indicates, this is about the MAT stands for MATLAB. So those who are habitual using MATLAB actually, because MATLAB is very easy to understand, and there are many toolboxes, image processing toolbox. So in the image processing toolbox takes care of all image processing operations. Only you have to use the function. Okay, like hist is one of the function. Hist, so hist will call hist bracket I. Okay, this MATLAB command will give you the histogram of the image. You see such a complicated operation. We have only one line code. Okay, or one line function. So those people, if they want to use a deep learning, so that's why there are deep learning libraries people have developed, and that is a MatConvNet library. Okay, so other libraries are there actually. Okay. This is about the performance. We can measure the performance using confusion matrix. That is a true class and predicted class. So this most of time, this is one of the tasks actually in the medical image. That is a classification operation. We want to classify whether person has COVID or not COVID. So you can see person has a COVID and he predicted as also COVID. So that is good, that we expect. So here we want actually 19, more than very good accuracy, 98, 99 accuracy. If person is a COVID, actual class is a COVID, and if he is detected as a non-COVID, so what is the problem? That person will not be treated actually, okay? So person has a disease, but we are not giving treatment. So that is a wrong. So we want a very almost zero number here actually, okay? False negative. If person is a non-COVID actually, he don't have COVID, but detected as a COVID. So unnecessary, we are giving the treatment actually. Healthy person, we are giving the medicine. So, okay, this is also not acceptable. And a person has not COVID and he is detected as a not COVID. So this is okay. So we want this. So true negative. So true positive and true negatives, we want 100%. Okay. So based on this, actually, there are some performance measure like accuracy, sensitivity, precision. So these equations are there. Okay. So now we will discuss one application actually of this. With this background, we have discussed deep learning, we have discussed medical image processing area. Now we will discuss how this can be used for COVID-19 detection. So here you can see we have used. So here I'm going to discuss some work actually which we have did in our lab. So you can see this is a CT image, okay, of the person. So here white arrow indicates GGO. GGO stands for ground glass opacities, okay. So you can see there's one picture or one CT image A and another is a B. So what is the difference between these two? So first image actually this captured at the initial stage when person was infected. So you can see here this gray region, which is called as a ground glass opacities. So that was a small actually in the lungs. Black region actually black, this color indicates healthy. So there is no infection, okay. So this is the image of the lungs and this black region is the healthy region and this gray is the ground glass opacities, okay. Now in a second image, you can see there is an increase in this ground glass opacity. So this image is taken after the infection, maybe after a week actually from the infection. Okay, infection started and you can see the spread of the infection. So this spread is more actually. So to detect actually how much spread is, so for that purpose, we can use a segmentation operation. And first operation is a detection actually. Detection of this ground glass opacity is called as a detection operation. At which part of the lungs, that operation is called as a localization operation, okay. And how much is the infection? So that information we can get from the segmentation operation. And where is the classical operation? So we are this actually we have detected the gray region. So this gray region is a COVID coronavirus infection, and black is the. So in this way we should be able to classify into two classes. Okay. So we're going to discuss those things in the coming slide. Okay. So here actually 75% covered patient has a crazy paving in the CT image. Okay. So we want to detect this. We want to automate this operation. Actually here a doctor actually asked for CT image. Then by looking at the CT scan, he can say the person has infected. Okay. Then he will go for the after week actually. So here he can comment, okay, that infection has increased actually, okay, and it's increasing continuously. Okay. So this type of comment doctor can make, but we want to automate this. For that purpose, we are going to use a deep learning techniques. Okay. So this is the research gap actually we observed. So most of studies have used very small amount of data. Still, this is a problem actually. People wanted to work in this COVID-19 detection, but they are unable to get the data. Okay, online data is not available, and that is a problem. And what is available actually is in the JPEG format or PNG format, actually not in the raw format, or CT scan images are not there. Okay, so that is a problem. The network develop are complete. There are many deep learning networks people have proposed, and they published the paper. Okay, since there was no paper or no reference for this actually before 2019, so many papers are accepted also, because at least whatever small development in this area people want to address actually, and in order to get a benefit to the society, uh, publishers have accepted such papers. Okay, initial papers. And but nowadays, now we have to come up with the very good deep learning network actually. So that is a challenge actually. So you can work in that area. So that is a research gap. Okay, we want computationally, we want to reduce the computational cost. Okay, and propose a network accordingly for this special problem, specific problem. Another is hurriedly people publish papers, people work on this COVID detection, but there is a little development in the enhancement. They have not used enhancement in the image. Whatever image they got, actually they process and conclude, okay, whether it is a Corona-19 infection or not. But if you perform some pre-processing task actually before using the deep learning, if you do some image processing task to improve the quality of the given image, and then we can see address improvement in the classification, and even we can reduce the cost of the computations. We can reduce some layers also. Okay, because if quality of the image is good, then we may require less number of layers. Okay, or less cost. So these are things. So there is a research gap. And a lot of papers actually they have used the transfer learning. So what is a transfer learning? Means model was developed for some other reason. Model was developed for vehicle classification. But we are in a hurry actually. We need a COVID-19 detection as early as possible using some deep learning technique. So what was the trend actually? People started using the already developed model actually for some other application. Like application was vehicle detection or vehicle classification, whether it is a car or whether it is a truck or whether it is a bus. So model was developed for that. They want to use that whether input image is a COVID or non-COVID. You can see the change. So, and so people have to tune the model, already existing model, and use for the detection purpose. So that technique is called as a transfer learning. So model is developed, we want to modify the weights according to our problem. So we'll tune that model for COVID detection. So instead of images of the car, now we'll give the images of the lungs, okay? And that too is CT images. That time we have used the JPEG images. Here we can use DICOM images, okay, CT images. So these are the research gaps. So you can work in this area if anybody want to start research. Okay. So research questions to be answered. So that time we targeted these questions. First is, can image enhancement technique provide improvement in the diagnostic accuracy? Actually, intuitively we can say definitely, if we have good quality image, definitely we can detect infection very good. Okay, we can see the improvement. So that we know, but we'll check experimentally. So that we have done, and we'll see, discuss actually. Okay. Then second is, how significant the performance boost provided by using a deep learning approaches where traditional handcrafted descriptor. So here what I want to say, traditional handcrafted descriptor means features are extracted using some feature extraction block. Okay. And that we can compare with the deep learning, or even machine learning techniques we can compare with the deep learning, and we can say that there is improvement in the performance based on the experiments actually. So there is a scope to improve. And for deep learning, there is a overfitting problem, because if we give the fixed same images, like we have 100 images from one hospital, from your city, 100 city images. Out of that, you use 80 images for test, for training purpose, and from same set, if you are using for testing, you may get a good accuracy. Okay. Now question is, now your model is ready, and if I want to test the images taken at from other country, okay, and in a different environment, so definitely I may not get a good accuracy. So such a problem is called as an overfitting problem. If input testing images are exactly matching with the training images, then we will get a better accuracy. And if there is a slight deviation, your model will say, okay, it's not a COVID, it's no COVID case. Okay, because we are given a very good COVID images, and if there is a slight change, model will not accept. Model will classify something different. But that is wrong. We know that this need to be treated. Okay, so that's why we have to use a regularization problem or some other techniques. So that is a overfitting problem. So these three problems we will address in the forthcoming slide. Okay. So we have proposed CNN plus SVM framework. So here you have to understand, as I mentioned, initially people have not used the pre-processing technique. Directly they process the image, but we are using here pre-processing. So through pre-processing, we can enhance the quality of the image. After that, we will use the model. Okay. So we can propose our own model, or we can use the existing model actually. Okay, and that is called as a transfer learning. We can use a transfer learning. Okay, again in the model also we can have fully connected layer as the last layer for the classification purpose, which will have two neurons as output neurons. One is a COVID, another is a non-COVID. But if we can remove that full last layer also, and we can use again machine learning algorithms like a support machine NK. So this type of variations we can do. I have discussed various variations. So we use this data set, SARS-CoV-2 city data set. You can see images are in the PNG format. This is a COVID-19 class, and this is a non-COVID class. Okay. So you can see actually, here you can see there is a ground glass opacities or gray region. You can see there's a lot of infection. You can see first city image. Second city image, there's a little less infection. Only this part is infected. Here you can see everything is a black actually. Okay, black regions is more. So there is no infection. Okay, so it's a healthy person, is healthy actually, non-COVID class. In COVID class, there is a ground glass opacity or gray region. Okay, so that's why it is called as a ground glass opacity. So it's a COVID class. So you can see the image given is in the PNG format. Okay, so these are already compressed images, and whenever we are performing compression, we are going to lose some information, which we cannot afford with the medical images. But unfortunately, we don't have proper databases available. So we have to work on these images, at least at this point of time. So this is one case. Okay. So pre-processing step, actually you can do image processing. We can apply image processing. One of the processing technique is a contrast enhancement. We can improve the contrast of the image. So that will help you. Okay. So I will discuss directly results. So this is the original image and its histogram. So what is a histogram? Histogram gives estimation of number of pixels belonging to particular gray value. Okay. Since these are the black and white images, means monochrome images, and they have intensity values varying from 0 to 255. Then we will compute how many pixels are having intensity 0, how many having 1, how many having intensity 2, how many having intensity 255. Okay. And if we plot that number versus intensity values, okay, that graph is called as a histogram, okay, in image processing. So you can see from this histogram of the original image, this region 0 to 60, I think there is no very less number of pixels. Then again 100 to 200, very less number of pixels. Most of the pixels are between these, say 60 to 90 region, okay. And then this maybe 180 to 240 in this area. So this is a so here there is a need to stretch the contrast. So how can we stretch the contrast? Stretch the contrast means we should have all intensities present in the image. Here actually this intensity has 0, so we'll stretch this towards the 0. So you can see contrast stretching stretch towards the 0. Okay. So by using some analytical or some equation, okay, some function, monotonic increasing function, we can stretch the contrast. Okay, so this is the result, but still it is not good. Okay, so in histogram equation problem, you will find most of the intensity values are present, and also significantly available actually for this region. You can see 5 to 50 to 100 intensities, number of pixels are very less. Now here they have increased actually. So histogram equation means we are going to make a number of pixels equal for all intensity values. So that is our target. Practically it's not possible. By applying this histogram equation algorithm, you will get this histogram and corresponding image actually. You can see here. So this image is also not good image, histogram equation image, even worse than the input image, you can see. So a lot of gray region, and you will declare it as a, or classify it as a COVID region, okay. So that's why we have used a Clahe technique, okay. So you can see this histogram. So here the peak actually we are going to clip, okay. So H stands for histogram, E stands for equalization. So it's a modified histogram equalization technique. A for adaptive, and C for clipping, actually clipping level, okay, of the histogram. So that is a Clahe. You can see the results of the Clahe algorithm on other image, okay. So in this way you can improve. Here you can see only few intensity levels are present. So there's a need of stretching. So these are stretching techniques. 3 techniques are used here: contrast stretching, histogram equalization, and Clahe. So we can use one of the technique to improve the quality of the input image. But Clahe is giving better. So that result is presented in the paper. So these are the different images, 4 images, and their enhanced version is shown. Enhanced means improved quality, or contrast enhanced version is shown. We can measure PSNR value just to understand the quality of the output image. So you can see PSNR value is higher for Clahe. Other cases it's lower. Okay. After that, for extracting features, we can use a GLCM technique, like a gray level co-occurrence matrix. You can see here. So what is a gray level co-occurrence matrix? So let us assume this is the image segment. This is the image. And for this image, we want to generate the GLCM, gray level covariance matrix. Okay. So what is the size of this matrix? If input image contains intensity values from 0 to 255, then size of the GLCM is 255 by 255. So here actually we cannot draw this big matrix, and for simplicity I have taken a small image set and range also only few intensity values. So here we have considered only 5 intensity values. So intensity from value is 1, 2, 3, 4 and 5. So only 5 intensity values we have considered in this image. So they are available in the image. So gray level co-occurrence matrix size will be 5 by 5. And then how to compute each element of the matrix is explained here. So the procedure I will directly explain instead of giving analytical equation. So here 1 followed by 1, how many times is occurring, that we have to compute, measure. So it is occurring 2 times. So we'll write here 2. 1 followed by 3 is 1, followed by 3 is 1. Okay, 1 followed by 2, how many times? 1 followed by 2. So here there is 1 followed by 2. And here there is 1 followed by 2. So 2 times, so that's why I written here 2 times. 2 followed by 4, 2 and then 4, 2 and 4. 2 followed by 4 is 1 time. So that's why 2 followed by 4 is 1 time. 1 followed by 4, 1 followed by 4 is not there. So it's a 0. In this way, we can compute a GLCM. Here we are considering horizontal. That's why angle is 0. So we can have GLCM matrix for 0 degree. Similarly, we can have a GLCM matrix for 45 degree. 5 followed by 2. 5 followed by 2, say 2. In this way, that we have to decide actually. Okay, so you have to decide which degree, okay, you are going to use for extracting GLCM features. Okay. Okay. So this is about the features. Okay. We have proposed one baseline model. So this is the model actually. Model means actually what? Model contains input layer, output layer, then convolutional layers, max pooling layers. Then while deciding the model, we have to decide number of neurons in each layer. Then max pooling operation we have to fix, whether it's a max pooling or average pooling. For convolution operations, we have to decide the size of the convolution mask, coefficients of mask. Okay, so all those things we have to decide, and then we can propose the baseline model. So we have proposed such a model. Okay, and their accuracy is reported here actually. So you can see here accuracy is in the training phase it's a 60%, and validation phase it's something around 68%. So accuracy is not good. Okay, whatever proposed by us is not good. So we want to improve that. Okay. So we have used the pre-processing technique or histogram manipulation technique. You can use a CLAE also. Okay. Technique, so that we can get a more accuracy. So accuracy is little bit increased. You can see accuracy of between 60 to 65% for training. Here accuracy is up to 90%. You can see. So pre-processing image, pre-processing definitely improves the performance. Then next is a transfer learning. So it is called as a network on a steroids. Now during COVID we have heard this word steroids. Okay, steroid means energy boosting, something ready-made actually will cure. So that's why some people are using this term for transfer learning. So already something is ready. So this is the ready. We just transfer this for our problem. And why it is required? Because sometimes we don't have large data available for that domain. Same case for COVID, we don't have much data to train the model. So already we are trained with some other data. Only we can twin that model for our application. Okay. So this is the transfer learning. Second thing, we can save time, training time we can save, because already model is trained. No need to start from the scratch, okay? So there are many advantages of the transfer learning, and that's why you'll find many papers, okay, COVID-19 detection papers using transfer learning. We also use one paper, one model. So MobileNet V2 model we use for COVID-19 detection. So you can see MobileNet V2, as name indicates, mobile. So that model was proposed for the smartphone, and that's why something we want to use for the smartphone. Smartphone is an edge device. So there we have to use a less number of layers and computationally cheaper model. Okay, so MobileNet V2 was one of them. Okay, so that's why we selected that. You can see MobileNet model was trained using ImageNet model. ImageNet model was introduced in 2012, and after that model, ImageNet model, it's a breakthrough. Okay, after that, actually, we have achieved a lot of milestones in the deep learning area. Okay, so what is the beauty of this model? It's a very huge model, millions of images. And how many classes? What is the variety? So this image has 1,000 classes. There are some images of sea lion, Egyptian cat, Indian elephant, or tractor, okay, go-kart, so many. Such a 1,000 classes are there, okay. So the model was trained on ImageNet dataset. Now same model we want to use for our COVID-19 detection problem. So here you can see there they have used a 10 million images. Now we are going to use a 2,500 or less than 2,500 images, okay, for training purpose. And these layers we are going to use, 15 layers we are going to use as it is, okay. Only we have to propose this block 16 and con 2D and batch normalization, last this blue and green color, that we have to twin. So what we'll do, we'll give input image, okay, and we'll see the output class, okay. So if output class is COVID, input image is also COVID, then we'll not modify any weight. If input image is a COVID and output image is a non-COVID, then we'll use a back propagation technique. We'll go back actually, and we'll update the weights, okay. And which weights we'll update? We'll update the weights of the block 16 only, and these weights. Other weights are frozen weights, okay. Similarly, we'll train all the images, okay, all the 2,500 images of the data set, and we can update the weights. So this is called as a fine tuning, okay. If the model purpose is difficult to achieve, we can introduce another block, block 17 we can introduce. In this we can keep introducing blocks, okay. But we will not disturb actually this already trained, pre-trained weight, okay. Those are called as a frozen weights, okay. And through this also people got very good accuracy. There are many papers on transfer learning and same data set with a very good accuracy, more than 90% or something. So here actually another problem, we can use cloud layer or edge layers, cloud and edge layers. So here actually this application we proposed. So there is a data layer, which we have CT images of the patients. So, and we want to use the mobile phone, okay. If we're going to use a mobile phone, then we can get a GPS location, okay. We can ask him to upload his CT image, person CT image on the mobile, and whatever algorithm we are written, we will run that algorithm, execute that algorithm on mobile itself, and we'll detect whether the person has COVID or not. If person has a COVID, then there was a requirement actually from the government side to know the number of COVID patients in the particular region. So if we send actually only his location, his name, to the database, okay, which is available on the cloud. And the database is accessed by whom? That hospitals will access the database, government agencies will access this database. What they will obtain actually from this database, okay, available on the cloud. So government can decide actually mobilization of the resources. In particular region of the city, there are many patients. Then they can depute many doctors, many ambulance, okay, many resources on that area, okay. So that's why it's called as a COVID-19 management. Okay, not only detection is important, we have to manage the resources, okay, manage the patient's data. So that is one thing. Second thing, we can send the doctor actually to this patient, and we can treat the patient. You know, the COVID is a communicable disease actually. So it will be good if we handle the patients remotely. So the further purpose again, we have to send this as CT image to the doctor. To avoid the bandwidth, instead of sending the original CT image, we can send the processed CT image directly, segmented CT image to the doctor, or some part of the image, so something like that, okay, to reduce the bandwidth, okay, to reduce the transmission cost. So this type of techniques people proposed actually to handle the COVID-19 infection and to manage the outbreak, okay. So this is the smartphone, this is the image, and alert will be same. Whenever COVID-19 is detected, without waiting actually, immediately his location will be sent to the government agencies immediately, so that proper action can be taken for the management of the COVID. Mobile net feature advantages, number of computations are reduced actually. So they use a depth-wise convolution and point-wise convolution, okay, these techniques. So if we use a fine-tuned mobile net feature, you can say this is the accuracy we observed. During training, it's almost 100% accuracy. While validation is between 0.9 to 1. Okay. So this way we have improved the accuracy. These are the numbers. If patient is COVID detected as COVID 240, so 10 cases there is a problem. Okay. That number we want to improve, and that number is improved in the SVM classifier. You can see their number is 4. So COVID is detected as a non-COVID. So here these 4 patients will not get a treatment because they detected as a COVID. Okay. That is one case. And here we want this number also reduced. Non-COVID is detected as a COVID. So these people are taking the treatment unnecessary. Okay. Nowadays these cases are more actually this third phase. Actually symptoms are not that much severe, but still there are many reports saying that person has a COVID and we have to admit the patient, okay, or we have to quarantine the patient. So this is the performance. So I have summarized here performance of our work. So we started with the original GLCM KNN classifier. So this is the machine learning technique. So we have not processed the image, but we have used a gray level co-occurrence matrix for extracting features and KNN classifier, and you can see the accuracy 85% or in between this. Okay, first graph is accuracy, second is a precision and sensitivity. So if we use a CLAHE for pre-processing technique, even simply by doing a pre-processing, we can have some improvement. Here there is no improvement in accuracy, but precision is improved a little bit. Sensitivity is also improved, okay. But there are more chances to improve accuracy also, okay, by using the CLAHE technique, by properly tuning the algorithm, okay. Here you can change the clipping level actually, and test whether the accuracy is improving. So that you have to do. Okay, after that, actually, then we decided to use a deep learning, and we proposed some simple model, baseline network, and we observed the improvement in the accuracy. Then we proposed MobileNet V2 model and this pre-processing technique, and you can see the improvement in the accuracy. Then we decided, we thought that why to use a fully connected layers for the classification. Instead of that, can we use a support vector machine? So here we are mixing deep learning with the machine learning, okay, fused combined approach actually. And we found improvement in the accuracy further. And then we have decided to change the machine learning algorithm. Instead of SVM, can we use the KNN? And we observed a drastic improvement, more than 95%. So you can see, so you have to do the research this way actually. We start with something that keep on continuously improving, okay? You keep changing the modules. So we started with the machine learning algorithm. Okay, then we use the pre-processing block, Clahe, to improve the accuracy. Then we switch to the deep learning by using baseline model, our proposed baseline network, but that proposed is not good actually. So we use a ready-made or steroid kind of thing, ready-made available model, MobileNet V2, and we observed the improvement accuracy. We didn't stop that point also. Then we thought whether we mix, okay, SVM or machine learning with the deep learning. So we remove the last layer, fully connected layer. We use the SVM and we observed very good accuracy. And then we have used the KNN. So this is, in this way, actually, we have seen the continuous improvement in the accuracy. Okay, whatever proposed is the best actually. We tried many machine learning algorithm, but we observed good with the SVM. So SVM is reported here. So this way we can improve the performance. Okay, so data set requires deep learning requires a massive amount of training data set. Unfortunately, such a data set is not available for COVID. So whatever data set we have available, we are working with it. Okay. So unavailability of data set is one of the biggest barrier in the success of deep learning in medical imaging. And also, unlike other data set like sports video data set or vehicle data set, medical data sets are not available online because of many reasons. One of the reasons is ethical clearance. Okay, we have to take the clearance from the patient's hospital for publishing data set. Okay, so that is also one of the problem. And but still now people started sharing medical imaging data set. Okay. So I have listed actually some data sets for you. These data sets are available online. So this is the list actually. I have collected different data sets. So ILD, ADNI, DDSM, STAYER, HVS EMR, okay, ISIC, OAI, BRATS, Drive. So out of this data set, we have worked on STAYER data set, Drive data set, BRATS data set. These are very popular data set. So these data sets are with a different image modalities like CT image, MRI image, mammograms, JPEG image. Okay, these are the different data image modalities, and these are the different anatomic site: lung, brain, breast, eye, etc. And these are the different tasks actually. So you can say, for example, this eye data set, STAYER data set, and Drive data set actually. There are two data sets for eye, and they're used for the segmentation purpose. Okay, if I want to use image processing for brain tumor detection. Okay, so ADNI data set or BRATS data set is available, and they have used MRI as a modality for brain tumor detection. You can see, but their intention was different actually. This ADNI data set was developed with the classification task. Okay, and this BRATS data set developed for segmentation purpose. So all these data sets are the open source. They are easily available on the online. So you can download and you can use. Okay. Like a deep learning, we have seen ILS, VRC challenges, and every year they perform this, invite the paper. They share the data. They share the ImageNet data set. That's why ImageNet's data set is available for everybody online. You have to work on ImageNet data set and participate in the competitions, and winner actually. That winner model will be selected based on error actually. The model has less error and a less number of layers actually. But error is a priority. Error is less, and then we'll go for the layers, number of layers used. Okay. So this is there. Okay. So similarly, for medical imaging also there are many challenges like BRATS 2018. So you can participate in such challenge. So the people are organizing competitions. So they share the database. That's why they share the database. They ask actually you work on our data and produce result and you publish paper. Okay. And by that process, we will get a new algorithm. So that's why they encourage people to work in this area. Okay. So BRATS is the brain tumor detection database. So the BRATS 2018 competition was held. So that group will hold competitions frequently. After 18, I think I don't know when it was published, conducted. Okay. Then Kaggle's data science bowl 2016, they have a data set. So they work on the heart disease. There is another competition, ischemic or stroke lesion segmentation. Okay, this is related to the heart attack. The pneumonia detection, lung opacities actually. You know, for COVID actually people started using pneumonia technique. Okay, people most of time people refer to pneumonia because for pneumonia also we have to check the lung opacities. Okay, so these are the different challenges. So you can participate these, or at least you visit their websites, you will get a lot of material available. First, you will get the data set, and second, the popular algorithms also with their achievements. How much accuracy, how much loss, how much layers, okay, all those things will be there. Then, what are the challenges using deep learning? So I have listed the challenges. Some challenges we discussed also. One of them is a limited annotated data. First thing is a limited data. Now I have next is a limited annotated data. What is annotated data? So I have thousands of CT images, but I don't know which are the COVID images, which are the non-COVID images. Then we have to label actually COVID, non-COVID. How to label this? Then we have to ask the doctor actually. Okay, you see this by your eyes, this CT image, and then you can say COVID and non-COVID. Okay, so in this way you can annotate. So annotation is a time-consuming task. Okay, so first we don't have data, and secondly we don't have much annotated data, labeled data. Okay. So this is one problem. There is another problem, is a small data set. Size of the data set is small. Then there's a class imbalance problem. What do you mean by class imbalance problem? So I want to classify as a COVID and non-COVID. And I have to collect the CT images. So it's okay nowadays because of the corona pandemic situation. You will get a lot of COVID images, but the healthy images are rare actually. Okay. So because nobody will go for CT image without, so you have to pay to the patient actually. Okay, you have to encourage the patient, encourage the subject that I want CT images of the healthy. So in your database, let us assume that you have 50 images of the COVID and 10 images of the healthy. So such a situation is called as a class imbalance. For training, we require equal number of images. So 50 images of the COVID and 50 images of the healthy person. So how to handle that problem? That is also one of the question. We will discuss that. Second is a overfitting problem. That for training phase, we are using a very good quality images, and testing actually we want to test practical images. Okay, so it's called as a overfitting problem. Like face detection, biometrics based on face detection. While developing the database, okay, if I want to see whether the employees, whenever employee enter in the office premises, we will have his face, and we'll detect, we'll mark his attendance. Okay, we have this system. So what happened actually, while training phase, while developing the model, people give very good quality images, close up, good quality, etc. And when during the implementation phase, actually, the person is sometimes person fails to sometimes maybe because of the weather, fog or environment, his appearance actually, the quality of image may not be good. And that times there are chances actually that person may be said that, okay, you are not person X. Though it's the image of the person X, but our system is saying you are not person X. So this problem is called as an overfitting problem. That's why in the database itself, actually, we have to give, while training, we have to introduce such images. Images taken into the during the different weather conditions, different lighting conditions. Okay. So this is about the overfitting problem. And the training time, this is true. If the data is large, we require a large training time. So how to handle this? So there are some solutions which I'm going to discuss. If data is limited annotated data, then you search for online annotated database. And you can use that for training actually. Okay. Second is a small data set. So you can make a big data set by using a small data set by introducing data augmentation technique. So if input image is there, we just change its, rotate that image, and in this way we can increase the size of the data. Or secondly, you can have, you can scale it actually, scale. You can reduce the size of the image, face or size of the person. Okay, that is called as a scaling operation. So you can scale, you can rotate, you can move the object in the image. Okay, object is at the center. Now you can shift to the one of the corner of the image. So that is possible. So all these techniques are called as augmentation technique. And not only they solve the problem of the data set, they solve the problem of the overfitting also. You see, overfitting is because of that only. Okay. So this is the problem. Second is a class imbalance problem that you can solve by data augmentation technique. We can introduce more positive samples by augmentation technique. Class imbalance problem is also solved by patch-wise training. So, okay, we have limited images, like 10 images. So in training, actually, we will not give input as a full image. Each image will divide into 10 parts, okay? So 10 images, and each image is having 10 parts. So how many patches will be there? So there will be 1,000 patches. So now we are training with the patches instead of training with the images. Sorry, 100 patches. So initially training was performed on 10 images. Now we are performing training on the 100 patches. Okay. In this way, we can improve the, you can solve the class imbalance problem. Okay. Next is a, okay, overfitting problem that we have seen. We can have a dropout layers. We can drop some layers. That is one thing. Even we can drop some neurons. And these dropouts will introduce some probability, some uncertainty, and that helps to solve this overfitting problem. Next is a training time. Okay, so one of the earlier solution for this issue is to apply pooling layers. So you can see, if we use a more pooling layers will reduce the size of the image or size of the matrix. Okay, so ultimately dimensionality will be reduced, and that helps to increase the training, reduce the training time. Okay. Also, while pulling, actually, we can have a higher stride. Actually, stride means shift. Actually, okay. So that also helps a little bit. Batch normalization. That is one thing. Second thing, pixel values also we can subtract mean from the pixel values. Okay, mean intensity of the image from the all pixels. Okay, so that our numbers will be small. Actually, multiplying 256 by further multiplying 256 by 33, this number, so it will take a lot of time. But if I multiply 2 by 3, so that's easy operation. So in this way, we can reduce actually the numbers by subtracting mean from the each pixel value. So these are the techniques. Actually, these are not standard techniques actually, but people try this, and most of the time this work also. Okay, these techniques useful also. Okay, for better. Okay. Secondly, where to start actually? So this just I'm going to suggest this actually. If you are in the beginning level, so you can start with the Kaggle and other open competitions, and use existing pre-trained networks like Google Net, like a transfer learning, and can work. Okay, this is for starting purpose to create the interest in the deep learning for image processing. And then after that, you can experiment with the model specific to the image medical imaging, and like UNet and FINET you can use for this medical imaging purpose. Then combine 3D party data for greater insight. So database you can change. In this way you can keep experimenting. Okay. So after that, actually you will become an advanced learner. So that time you can propose your new model. Okay, that is level 3. In this way, level wise, if you study, you will be a very good learner, deep learning learner. Okay. Advanced means here you can experiment with building new models from scratch. Okay. So level 1 and level 2 we are using the ready-made models. Level 3 we are starting with our own model. And at level 2, level 4, then it's a mature. So there we can experiment with a lot of techniques. You can go for the reinforced learning. You can introduce many feedback loops in the model. Okay, you can industrialize the ML and DL pipeline. You can share model repository across countries. So this is the journey. So I have given the outline. Actually, this is up to you. It's a person to person. It depends on the person. So one of the paper, actually I presented work on COVID in this presentation. So you can refer this paper I recently published, that deep learning empowered COVID-19 diagnosis using chest CT scan images for collaborative edge cloud computing platform. So here we have used deep learning, we have used edge cloud computing platform, and we have used CT scan images. Okay. So you can refer this paper also. Thank you. So any question?
Yes, sir. Yes, sir. So we have some question. What is the dense in the CNN diagram?
Oh, okay. Can you tell slide number?
Yes, Raghav Tiwari, are you there, Raghav?
No, no, okay, I understood. I think he may be asking on this REST-net, actually, dense net.
Yes,
So I
dense
think
in the CNN diagram. Actually, sir, I thought there is a slide. I think in the 5th or 6th position it is there. CNN. It is about CNN.
okay,
5th or 6th
but
number slide is there. Raghav?
okay, can you speak?
Raghav, are you
You
there?
asked.
So, any participants, do you have any more question?
Okay, let me explain dense net because he has asked.
Okay, okay, dense net.
So dense net, as the name indicates, it's a dense, means there are many layers actually. Okay, you can see. So this is here you can see how many, 152 layers actually. Okay. This is the development in the REST net.
So
Dense
screen
net
is
is the
not visible. Screen is not visible.
okay. I have not shared. I think Okay. Now it's visible.
Yeah. It is dense net. Yeah.
Actually, you can see there's a improvement in the error because of using more and more layers. Okay. So dense net means number of layers are more actually. Okay. Initially, previously only this much model was there actually. So if we have such a many models, okay, X0, X1, these blocks, and each block has a many layers. Okay. So they have increased the number of layers drastically, and that's why it is called as a dense net. Dense net is okay. These are good for error point of view, but very difficult for implementation point of view and hardware point of view. Okay, so that's all. Any other question?
Yeah, participants, if you have any question, please, you can ask the question. Participants, you can unmute yourself. Yes, Dr. Santosh Singh sir. Sir, you can ask your question. You please unmute yourself. Yeah.
Yeah. May I audible?
Yeah, sure.
Yes.
Sir, one thing I wanted to know in the CNN, right? So till the process of pooling,
Right.
finally you are providing input to the all the inputs to the neurons, right?
Right.
So before feeding the input to the neuron, you can say that is the kind of data pre-processing.
And before, say again.
Before giving the input to the neurons,
Okay.
that process can be say data pre-processing in the machine learning, in the terms of machine learning.
Okay, that you can say pre-processing. Means, or in other words, you can say instead of input, we are going pre-processed input actually. Okay.
Okay.
We are talking about the first layer. Input is X0 to Xn, for example, X0, X1 up to Xn. These are the,
I mean to say, before providing the input to the neurons, you can say all the activity comes under data pre-processing.
okay, yeah, you can say.
Machine learning algorithm in terms of usual machine algorithm.
Right, huh.
So that's why you said convolution neural networks. What is the logic behind? What is the logic behind the convolution neural network?
Well, just I will share the PPT. Okay, PPT is visible.
Yeah.
Okay. Actually, there are two parts of the question. So this is the input. These are the neurons. Okay.
Yeah.
X0, X1 to Xn. These are the neurons.
Yeah.
So this is the input layer. Then, so such a many neurons will be there, and many layers will be there. Okay. Such a many layers will be there, and we are using a max pooling operation. Okay.
Yeah.
So there are two different operations. One is a convolution operation and another is a max pooling operation. So if we apply convolution operation,
But
input
one more thing, sir. At the last, just in this slide, you have providing the data of 1 into 128 matrix.
right.
So this can be say as a data reduction technique.
Right. So max pooling is a data reduction technique.
Okay. Just go to the previous slide, sir. No, previous one. That matrix. Yeah. This one. No. Yeah.
This one.
Yeah. This one. The the value of k. Where you have taken from this value?
This value is 0, 1, 1, 0, 1.
How do you have defined this value?
So this this is the key issue. This is important. Okay, like I want to generate a blurred image. Okay, we have an image here. Okay, I want to generate a blurred image for them, or I want to take the average, actually average of the neighbors. The pixel value is there, but I want to replace the pixel value by its neighbors. Okay, so for that purpose, then I can take all values are 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 for averaging operation. And so depending on the use, actually we select these numbers, actually depending on, like if I want to average, take the average, I can have all ones means what, actually this 0 multiplied by 1. Actually this problem, actually 0 multiplied by 1 plus 0 by 0 plus 1 multiplied by 1. In this way we will perform the addition of all these, okay, and divide by 9. So that is the average, and we will replace this pixel by the average. So average will come here if all pixels have value 1, 1, 1.
Okay.
Now, so actually that is the beauty. Actually, main thing, we're extracting features based on this mask. Actually, if we select the mask properly, we'll get the proper features. If mask is wrong, then we will get the wrong features. Like if I want to detect the edges, actually. Okay. So there people use a different mask for edge detection. Actually, some image processing concept is required here. Okay. So have you studied image processing course? Do you know, have the knowledge of image processing?
Yeah, of course.
Yeah. So you use Gonzalez and Woods book. Okay, Gonzalez and Woods for image processing. So there they have given different mask, actually. If I change this mask values, then this matrix will change, actually. Okay. Here, actually, for this region, because most of the pixels are 0, we will get a same value here. Whatever mask will change. Let us say see the mask is at this location. Okay, and we want to replace this pixel. This pixel means third number, 2 and 2 number. So this pixel means what, 1 into 1. Then and here also 1 into 1. So some new value will come, actually. So if we change this mask, here you also will have a new mask, a new image. Okay. One problem is this convolution mask. Here we have seen the reduction in the size, actually, but this is really not the reducing size dimensionality problem. Okay. Here, actually, for the corner pixel, if we align this mask at the corner, mask will go outside the image, actually. To handle that problem, actually, we can discard this first row and last row. Okay, first row and last row, first column and last column, because mask size is a 3 by 3. Okay. Now, if I increase the mask size, what will be the size of this image? If my mask size is a 5 by 5. Hello.
Yeah. I'm listening.
So what will be the size here?
If you increase the value dimension of k, that I into k will be increased.
Right. Here, if mask size is a 5 by 5, and if we centralize this mask here, then we have to discard actually first 2 columns and first 2 columns and first 2 rows, And by that process, we will reduce the size again actually. So one more row we have to discard. So 3 by 3 will be the output image. Okay.
Yes.
So this is one point we have to remember. And this is up to you actually. This is the skill of the programmer. Okay. That what coefficients we have to select. Ultimately, everything depends on these coefficients actually. Convolution operation, these coefficients are more important. So here actually I have taken binary image, but if it is a grayscale image is having different values, then if I change the mask here, the intensities will change actually. And depending on the application, if I select the mask as 111, so as if I am collecting 9 pixel values and dividing them by 9, so I will get the average value of the pixel, and that will give a blurring actually. You will get a blurred image. Okay. So that is that type of operation will be there. Okay. So do you understand, or should I? So it's about the and for pulling actually we are reducing the size. You can see for pulling we are reducing the size actually. Pulling operation. Here actually it's a problem because of that size is reduced. Here actually we are not reducing the size. We are going to discard those rows and columns. Or there is another technique that you pad number of zeros here actually. 2 rows you can pad with the 0 value. 2 columns you pad with the 0 value, so that you can align the mask here, and so you will get some low value here. Okay. So this is the convolution mask. Actually, this idea came from the signal and system course of the electronics or electrical engineering. People study signal and system course. So there they have to use a convolution mask. Yeah.
Okay, sir. Thank you.
Okay, can you mention?
Yes, any more questions from participants? If you have any question, please unmute yourself and you can ask. Yes, sir. So because we are approaching at 1, so I think we have to conclude the session, right? Javadan,
Okay.
sir? Shall we conclude? Okay, so thank you so much, sir, for unveiling the concept of artificial intelligence, which is really need of the hour in this COVID pandemic era, and Industry 5.0, in which the production model focused on the interaction between human and machine that aims beyond efficiency and productivity as the sole goal and reinforce the range and contribution of industry to society. Sir, your expertise in medical image analysis did reveals a lot, and it seems that you did a lot more in this domain. I am sure that our participants, those who are working in the vertical, those who are working in this vertical will be surely benefited from your talk. And yes, of course, our aspiring student get motivation from your talk so that they can accelerate themselves to work in this domain in their minor and major project perspectives. By making tasks easier, you explain the research gap. In your short talk, you reveals research gap, objective from where we can get data, competition, challenges, and whatnot. So thank you so much, sir, for sharing precious time with us, and thank you for giving this opportunity to listen you. And thank you so much for sharing your research experience with us. Thank you, sir. Thank you from IETE Student Chapter and from entire JECRC family. Thank you so much for sharing your valuable time with us. Thank you, sir. And participants, all of you are requested to please switch on your camera. Javada, sir.
Yeah, yes, ma'am.
You please take a group
Yeah.
photograph.
Definitely.
Yeah. And one more announcement to our dear participants, that tomorrow the session will be from 11 and will catch you at 11 by through the same Zoom link. Thank you so much, sir. Thank you
Thank you. Bye.
for sharing your time with us. Thank you.
Ma'am, thank you, ma'am.
Yeah. So participants, please will gather through this link tomorrow at 10:45 so that we can start our session at sharp 11. Thank you so much. Thank you, sir.
One
Thank
small
you.
little,
Bye.
more that tomorrow there is one short quiz after the end of
Yeah.
your session, so that we share the link on the chat box. So make sure that you all join the session also, so that you can answer the quiz questions. Based on that quiz, you got the certificate for the quizzes. Thank you.
We are not going to share any link for today's attendance. The same link which we will share tomorrow for quiz, and it will be counted as your attendance as well. So make sure that you all, those who are interested in taking certificate, please do attend that quiz also. Thank you. Thank you, dear participants, for your patience listening. Thank you so much. And thank you so much, sir.
Okay, thank you. So I will
Thank you.
leaving the meeting. Okay.
Yes,
Yeah,
of
sir.
course,
Thank you. Thank you, sir.
Okay.